Hello. In this example we're going to work through a usual kind of question. If you read the question, it wants to know the proportion of people who have an IQ greater than 130. We know the mean, we know the standard deviation. I would recommend that you always draw a sketch of the situation. So here we have a normal curve, the mean is at 110, and we want the proportion of people who have an IQ greater than 130. You'll note that the standard deviation is 14, which is the distance to the point of inflection, so 130 is further out in the tail than the point of inflection, so we know that the Z value is bigger than 1. First thing we need to do is to standardize the results. So the probability that X is bigger than 130 is the same as the probability that Z is greater than value minus the mean over the standard deviation. 130 minus 110 over 14. This turns out to be the probability that Z is greater than 1.42857. We need to try to find the probabilities associated with this value, so we'll have a look at the Z tables. 1.42 is here at 0.9222, and 1.43 is here at 0.9236. So we have 1.42 was 0.9222 and 1.43 was 0.9236. So we can see that this is actually a gap of 14, 22 to 36, and we want to go 0.857 of the ways through that interval, and 0.857 of 14 is 12. So really the associated probability for 1.42857 is 0.9234. This is the cumulative area below it, so the probability that we want is just 1 minus that, which is 0.0736. Part B asks us to find the IQ which is exceeded by double that number of students. Well, we had 0.0736, so 7.36%, and if we multiply that by 2, we get 0.1532. So really, what we're asking is to find the Z value which corresponds to a top tail of 0.1532. So if the top tail area is 0.1532, then the main body probability is 0.8468, and we need to find the Z value associated with this. So we need to look in the inverse tables, or try to find 0.8468 in the table and find the Z value for that. So 0.8468 is looking between 1.02, 0.8461, and 1.03, 0.8485. So 1.02 was 0.8461, 1.03 was 0.8485. This is a gap of 24, and I actually need to go to 0.8468, so I want to go 7/24 of the way through that interval. 7/24 as a decimal is 0.29, so technically the Z value is 1.0229. We would never have to be this accurate in the AP, but interpolation does work, and this does make sense. So that means that the IQ that we're looking for needs to be 1.0229 standard deviations above the mean. So the answer is going to be 110 plus 1.0229 times by the standard deviation, which was 14, and the answer turns out to be 124.3. Okay, moving on to the second big example, classic question which requires the use of the inverse tables and setting up a pair of simultaneous equations. First thing is to make sure you understand the question. If 87% of the sheets will fit through the gauge, then their width must be less than 8 millimeters. So what we have is normal distribution, and we know that 87% of the widths are less than 8 millimeters, and we also know from the other end that 7% of the sheets are less than 7 millimeters. So our job is to find the Z values associated with these probabilities. So first of all, looking at the 0.87, we need to try to find 0.87 in the tables, and it's actually around here. 1.12 is 0.8686 and 1.13 is 0.8708. So 1.12 was 0.8686 and 1.13 was 0.8708. This is a gap of 22, and I need to go 14/22 of the way through, which is just a bit less than 2/3. So the Z value really is 1.126. Clearly this is above the mean, so 8 millimeters represents the mean plus 1.126 standard deviations. Moving on to the second bit, 7% in the lower tail. 7% in the lower tail. We need to go all the way back to the negative numbers, and 7% lies around here, 0.0708 and 0.0694 at minus 1.4 ish. So minus 1.47 is 0.0708. And minus 1.48 was 0.0694. So we've pretty much got to go exactly halfway between the two. So the Z value for this is minus 1.475. So in other words, 7 millimeters is mu minus 1.475 sigma. Now we can now do this simultaneously and solve it properly, or we can just think about this in broad terms. This 8 millimeters we know is 1.126 above the mean, and this 7 millimeters we know is 1.475 below the mean. So altogether that is going to be the interval stretching from 7 millimeters to 8 millimeters. In other words, this gap of 1 millimeter is equal to 2.601 standard deviations, which you would have got through simultaneous equations anyway, and that therefore means that the standard deviation is 0.3845 millimeters, and then all we have to do is to find the mean. Well, if 8 millimeters was the mean plus 1.126 sigma, then 8 is mu plus 1.126 times 0.3845. In other words, 8 is mu plus 0.4329. Therefore mu is 8 minus that, which was 7.567 millimeters as required.